Welcome students. Objective of this lecture is to derive the conservation equations. By conservation equations I mean continuity equation, which is basically the conservation of mass, Navier Stokes equation, basically the Newton's second law, and the energy equation, it is the first law of thermodynamics. And all the equations we are going to derive under this assumption, as you can see, and all these assumptions I am going to show you when during the derivation, that why these assumptions and how these assumptions are used, and all these equations are in the differential form, and these are very important for the finding out of the field variables like velocity or the pressure or the temperature distribution. Now you can see that continuity equation and the energy equation, these two are scalar equations, and definitely Navier Stokes equation is a vector equation, and here since we have considered the 2D flow, that is why the two component of that vector equation actually written. So the first one is the x momentum equation and the second one is the y momentum equation. Okay, so let us start with the Reynolds transport theorem. We are not going to derive the Reynolds transport theorem, rather we will simply write the Reynolds transport theorem, and we are going to use this Reynolds transport theorem as a starting point of each derivation. That means derivation of continuity, momentum and energy equation. So according to Reynolds transport theorem, it is basically giving a relation between the property change with respect to a system and a property change with respect to a control volume. And if we consider B is some extensive property and beta is that property per unit mass, then this B is basically, if you consider a small volume dV, and if the density is rho dV, and if the property per unit mass is beta, then this particular quantity is what is this B, and beta is per unit mass, this particular property. Then according to Reynolds transport theorem, this dB dt, here this capital ddt indicates the material derivative or the Lagrangian derivative, that means it is at the system level. Okay, and that is equal to del t of the B of the control volume. This also can be written in this way also. So instead of writing B control volume, what you can write in terms of volume integral, you can also write like beta into rho dV, and this integration is over the control volume. And these two are actually not equal. This is what is the property change with respect to control volume, and this is what is the property rate of property change of the system, and these two are related, or the balancing term is this one, that is the surface integral of the property flux, net property flux that is going out of that control volume. So that is basically beta into rho v eta cap dA. Okay, so you can convert this surface integral into volume integral also. So for that, what you can do is that you can write this part as del t of rho into beta into dV. The dV part we are taking because we want to convert this quantity also as a volume integral by using the divergence theorem. As you know that to convert to surface integral into volume integral, we can use the divergence theorem. So if we apply the divergence theorem, this integration will become a volume integration, and what we are doing, this volume integration we put under the same integration sign, and this dV is taken common. Okay, and the whole integration is now the volume integration. Okay, so this particular thing, actually using the divergence theorem, we have converted into volume integral of divergence beta rho v dV. Okay, and then we have considered this thing. So here what here this integration is taken out of the del t, and that can be done only if this volume is not changing with time. This is what is the consideration. So now after this, what we can do is that we can use this particular Reynolds transport theorem to derive the different equation. Let us see how can we do that. So first we will start with the conservation of mass, and that is the continuity equation. So what we are going to do, we will put B as the mass of the system, and which also we can write in this form as rho dV integrated over the whole volume. And what is beta? That is the property per unit mass, which is basically 1 then. So if we use this Reynolds transport theorem, in the left hand side it was the material derivative of the mass at the system level. This is basically the B, and which is equal to del T of beta is 1 into rho dV, and integration of that quantity, okay, and plus surface integral of beta, which is 1 into rho into V into eta cap dA. Now if we just write it, under the integration sign, what you are getting is that it is del rho del T plus using the divergence theorem for the second part in the right hand side, that is rho V. Okay, so this quantity is integrated over the control volume. Now what is in the left hand side? The left hand side part is basically 0. This is what is the conservation of mass. So what is conservation of mass? Conservation of mass at the system level, we know that is equal to constant. So mass is equal to constant, that means the rate of change of the mass is equal to 0. So the left hand side part is 0. So definitely what we can conclude here is that this bracketed term has to be 0, because this del V, the delta V, the small volume that we have taken, is arbitrarily small. Okay, so arbitrarily any volume, and that is why if the function is not 0, it is not possible that integration of that will be 0 unless since this dV is taken arbitrarily. So del rho del T plus divergence of rho V, which is equal to 0. So this is basically the general form of the continuity equation, irrespective of any assumptions. Okay, now for this particular case we are going to derive it for the 2D incompressible flow, and let us see that what will be the form for the 2D incompressible flow. So first we are going to consider the incompressible flow. Now for the incompressible flow, the definition is that the volumetric strain rate is equal to 0, then we call that particular flow is incompressible flow. So this is our assumption, that incompressible flow, so this quantity is 0. Now we know that the density into volume is what is the mass of the system, since we are doing the differentiation at the system level. So that is why the Lagrangian derivative or the material derivative we are doing, you see. So if you differentiate both sides, so d dv dt plus v d rho dt is equal to 0. So it is quite clear that if dv dt, this particular term, is 0, then that implies, if this quantity is 0, which implies that d rho dt, this quantity, is equal to 0, because definitely this volume and the density, these quantities are non-zero. So d rho dt is equal to 0. So this is what is the definition of incompressible flow, we can write. See, this d rho dt is the Lagrangian derivative. Del rho del t is equal to 0. We cannot we cannot conclude if it is incompressible flow. Definitely if del rho del t is 0, it will be incompressible, but If it is incompressible flow, we cannot surely tell that it is del rho del t 0, because del rho del t, when we are doing, it is basically the density field variable, that is the partially differentiate with respect to time. So that quantity may not be 0. So I am not going into much detail of this explanation. Maybe in the interactive session we may discuss on it, but right now this is what is the definition of the incompressible flow. So already what we have seen, the general form of the continuity equation is del rho del t plus a divergence of rho v, and this quantity is 0. If this is the general form, then we can definitely write del rho del t plus what is this, v dot divergence of rho plus rho into divergence of v. Okay, so this is basically a kind of operator that is applied, and this particular operator is nothing but what is the material derivative. So the relationship between the material derivative and the field variable is that this d dt quantity is nothing but in terms of the field quantities is del del t into u into del del x plus v into del del y plus w into del del z. Okay, so if we restrict our discussion on 2D flow, so let us discuss our discussion on 2D flow, so that last part will not be there. So this quantity is what is del del t plus this quantity you can write as v dot del operator. Okay, so this is what is the d dt. So you can see what is d rho dt then. So d rho dt, only rho will come here. So this quantity is what is d rho dt. So here you see the same thing is here. So this quantity is actually d rho dt plus you see rho divergence of v is equal to 0. That means this quantity is 0 because of incompressible flow, and definitely for the incompressible flow is then divergence of v is equal to 0. So this is what is the continuity equation for incompressible flow. And for 2D flow, what we can write, the del u del x plus del v del y is equal to 0. So this is basically for the 2D incompressible flow what is the continuity equation. Now coming to the Navier Stokes equation, again we will start with the Reynolds transport theorem, and here we are considering the extensive property B as the momentum. Okay, and that can be written as also in this form, that velocity into the mass of a very small volume, and that if you integrate over the whole volume you will get beta, and beta is the momentum per unit mass, which is nothing but the velocity. Now if we again write the RTT, so from RTT Reynolds transport theorem, what we get is ddt of the momentum of the system, that is equal to del del t of this B. Okay, so that quantity is nothing but v dot rho dv, and this is over the control volume, and here this is basically the beta, plus over the control surface, that is the beta into rho v eta cap dA. Now what you can do, you can in a single integral you can write, if you convert the surface integral into the volume integral, and that will be del del t rho dv plus, here you can see this quantity is what, divergence of v rho v, and the whole thing into dv. Okay, now let us consider a very small volume dv on which we want to apply this particular Newton's second law. So what are the forces that is acting on this small volume? We are interested in that. Okay, so instead of this integration, we just consider, say, this particular volume. Okay, on this volume, what are the forces acting? So you need not to do any finite integration, because in our case the volume is this small volume only, this infinitesimally small volume only. So you can just simply omit this integration, because we want to apply, so our system or our control volume here is this small volume on which we want to apply this equation, because this is a differential equation that we want to derive. So differential equation means we are actually applying this equation at a point. So basically around that point we have considered a very small volume, and there what are the forces and what will be its mass, what will be its acceleration, the field variables that we are going to see. So what we are going to do, we simply omit this quantity. That means we are applying this equation for a small volume. And what is there in the left hand side then? The left hand side, this particular quantity is from the Newton's second law. What is Newton's second law? We know from the second law, from Newton's second law of motion, Newton's second law of motion, that rate of change of momentum, that means dp dt, the rate of change of momentum is equal to what? That is equal to the net force that is acting on the system, the net force which is acting on the system. So since we, in our case, it is a very small volume on which the total force that is acting, let us consider the net force which is acting is del F. So the left hand side part is the del F which is acting on this small volume, and the right hand side part is this one. I think this part is clear. Okay, now we can also simplify this the right hand side part a bit more, that we can write in this way, that it is del t of rho v plus divergence of v rho v, and the whole thing is multiplied by dv. We have only considered the now the right hand side part. So if you simplify, this quantity will be rho into del v del t. We are using the product rule, plus v into del rho del t, plus here we can write v into divergence of rho v plus rho v into divergence of v. Okay, the whole thing is multiplied by dv. So this is what is this part. Now if you just club these two terms, you see v bar will be common, and what will remain is del rho del t plus divergence of rho v. And what else will be this part and this part? If you take these two terms, then it will be a rho that will be common, and it will be del v del t plus v dot del of v. Okay, so this is what you are getting. Now it is clear that this part we have already derived. This is what is the continuity equation will give you. It is 0 from the continuity equation. Okay, and what is this part? This part you can see nothing but a material derivative of velocity dv dt. Okay, so basically what we are getting in the right hand side part is rho into dv dt into volume dv. Remember, what is the velocity here? We are considering 2D situation. The velocity is uy plus vj. Okay, so now let us see what is there in the left hand side part of the equation. Now left hand side part is, okay, one more observation. You can see this quantity, this part is nothing but the acceleration, because it is the Lagrangian derivative of the velocity. So this is what is the acceleration, and rho dv is nothing but mass. So left hand side part it is the force, and the right hand side part it is like mass into acceleration. So what is in the left hand side part is basically the force that is acting. Now this force acting on this small volume are of two kinds: surface force and body force. Okay, now let us first see what is the body force. Now this body force is, we are considering the assumption that only gravity is the body force. So we are considering the gravity is only body force, there is no other body force present, only body force present. So if the gravity is the only body force, so what is the net force, net gravity force that is acting? That is m into g. So m is what is rho dv, so rho into g into dv. So rho dv is the mass into g. This is what is the body force. Okay, where what is this g? Here let us consider in the x and y component. Say x component of g is gx and y component of g is gy. Okay, now what is the surface force? Okay, so for the surface force, let us go to the next page. Now delta F surface force we have to find out, and surface force will produce because of the stresses acting on the body. So if you consider this is the body, if you consider this is the small element, and say this is what is dx and this is what is dy, and let us consider perpendicular to the screen, the dimension is 1. So what is the volume of this element? That is dy into dx into 1. Okay, so this is what is the volume of this element. So what are the different stresses acting on this element? So first see what are the normal stresses acting. So definitely the normal stresses along x direction, you see this is the sigma xx. So what is the corresponding surface force then? This stress multiplied by the area. What is area? Area is dy into 1. This is the area on which it is acting, dy multiplied by 1. And what is the stress here? If the sigma xx is at this point, then what will be the stress at a distance dx along the x direction? Let us consider this is the positive x direction and this is the positive y direction. So stress will be sigma xx plus, using the Taylor's expansion, that del x of sigma xx into dx. So this is the stress that is acting at this end, which is dx distance away from in this positive x direction, and that stress multiplied by the area. What is area? Area is again dy into 1. Now let us consider the shear force. The shear force that is acting at the bottom surface, let us consider it is tau yx. Okay, so what is the force corresponding to that? Multiplied by the area, which is dx into 1. And what will be the shear stress here at the top surface? That is tau yx plus, along the direction y, positive y direction, if you moved by a dy distance, so it is del y of tau yx into dy, and now you multiply by dx into 1, which is the area. So we have only considered up to the first derivative, and the higher order terms we have neglected in the Taylor's expansion. Now these are the stresses which are acting in the x direction. Okay, now the stresses which are acting in the y direction also you can show. First you show the normal stress which is acting in the y direction. Let us do it by blue color. So it is sigma yy which is acting, multiplied by the area dx1, and here it will be sigma yy plus del y into sigma yy into dy multiplied by dx into 1. And what is the shear that is acting? Let us show it by black color. The shear force which is acting here, that is tau xy, and what is the area? That is dy into 1. So the shear that is acting here is what? That is tau xy plus del del x of tau xy into dx multiplied by dy into 1. Okay, so these are the stresses that is acting on this element. Basically, multiplied by area means basically these are the surface forces which are acting on the element. Now let us first see what are the surface forces that is acting along x direction. So delta F surface, let us consider its x component. So this quantity actually we have to find out. Let us consider the x component of that. So x component, basically here you can see it is the sigma xx, and here it is sigma xx plus del del x of this. So the net surface force in the x direction is this minus this, and you see sigma xx is going to cancel, only this derivative part will be there. So del del x of sigma xx and multiplied by dx dy into 1, which is nothing but dv. So multiplied by dv plus in the x direction, what else? Here you see tau yx dx1, and here this tau yx plus this. So tau yx will cancel, so only this part will be there. So del del y tau yx, that part will be there, multiplied by what? dy dx1, which is the dv. So the whole thing multiplied by dv. That is the net force which is acting on this small element along x direction. Similarly, you can write what is the surface force acting in the y direction, considering sigma yy and tau xy. And if you do that, what you are going to get is del del y of sigma yy plus del del x of tau xy into dv. Okay, now what is the del f then? It is clear that del f is basically del surface is basically del surface x I and del surface y component, that is the j. Okay, so now if now we are also considering that fluids are going to follow the Newton's law of viscosity. So what is the general form of the Newton's law of viscosity? Because this is one of our assumption that the fluid will be Newtonian fluid, that means it is going to follow this constitutive relation, that is the relationship between the shear stress and the velocity, or to be very specific, velocity gradients. Okay, it is not that this particular relation will hold for all the fluids, and this is the constitutive relations like Ohm's law, Hooke's law, like that. So there are materials which many materials actually follow this rule, so we are deriving for those only. So according to that, sigma xx is equal to minus p plus 2 mu del u del x, sigma yy is equal to minus p plus 2 mu del v del y, and tau yx and tau xy is mu into the cross derivative term, that is del u del y plus del v del x. Now if you put this stress values in terms of velocity and pressure, whatever you see, then this form, that is del f surface x component, that will become what? That quantity was this. Now what will be this component now? It will be del del x of minus p plus 2 mu del u del x plus del del y of del del y of yx, so mu into del u del y plus del v del x Okay. So now further we are considering the fifth assumption that mu is basically uniform. So mu is constant, we are considering mu is uniform, mu is not function of x, y, z. So you can take this mu out of this differentiation, or you can take this mu out of this differentiation. Okay, so kind of homogeneous material that we are considering. So for that what we are getting is that minus del p del x, that will be one term, and if you may take this mu out, then mu will come out, and what will remain is that del 2u del x2. Okay, and there will be another del 2u del x2 because there is a 2 del 2u del x2, so you can write mu into del 2u del x2. Okay, and what else? That will be, you can write here that this term, that means this term and this term, if you club, if you multiply, this is basically what? Del del y, if you just take mu out of del v del x. Okay, and that you can also write same as del del x of del v del y. Okay, that you can always write, provided second order continuity is there, you can always write this. So what that will lead to is that is mu into del del x of del v del y plus mu into del 2u del y2. Where from we are getting this one? The first part. That means mu into del 2u del y2. So first we have written this red part, and then the first part, this one. Okay, so if you now club these two terms, if you just try to club these two terms, if you just club these two terms, so what you are getting is that you just take common mu into del del x. What will be there is del u del x plus del v del y. Okay, and if you take these two term mu into del del x common, so this part is definitely is equal to 0 from the continuity equation, from continuity equation. So ultimately this delta f, sorry, then this delta f surface along x axis, this part becomes minus del p del x plus mu into del 2u del x2 plus del 2v del y2, that means the last term. Okay, so this is what is the del surface x. Similarly del surface y will be del f surface y, that term exactly in a similar way you will get minus del p del y plus mu into del 2 del x2 plus del 2 del y2 of v. Okay, and remember the whole term will be multiplied by dv. The same thing here also, I forgot to write that term every time, because that you have to remember, because whole term is multiplied by dv. Okay, so once you get that surface force and the body force, then you can definitely club these two terms. That means if you want to write this del f, then what will be that quantity? So del f you can write, so better you write in a scalar form, need not to write in a. So let us write now the x momentum equation. That means the x component of all these terms. So delta f of the x component, and that will be equal to rho into what was the term in the right hand side, if you remember, the term was dv dt into dv, so you just write the x component of that. Okay, so what will be the x component of this quantity? The x component will be rho into du dt into dv. Okay, because v you know is ui plus vg, so x component will be this one. So now this delta fx part, you just shift this quantities in the other side, so we write du dt into dv, and this delta fx part having the body force and the surface force. So what is the body force part, what is the surface force part? Let us write that. So this is what is the surface force part along the x direction. Okay, so write minus del p del x plus mu into del 2 del x2 plus del 2 del y2. This is u. This is what is the surface force part. Now what is the body force part? The body force part is rho into x component of that into dv. The whole thing, the dv will be there in all the terms, so you write in this way. Okay, so dv will cancel, it's clear. So you just write without any dv. So this is what is the x momentum equation. And what will be the y momentum equation? And this term you can also expand. Already you know what is this du dt. You know that this du dt term is basically del del t and u del del x plus v del del y. So here it is u. Okay, so du dt term is basically this quantity that you can write here. And what is the y momentum equation? Exactly in a similar way, rho into dv dt, which is equal to minus del p del y plus mu into del 2 del x2 plus del 2 del y2 of v plus rho gy. Okay, so this is what is the y momentum equation, and this is basically the Navier Stokes equation for these assumptions that under which this is the Navier Stokes equation. So in the next lecture we are going to see the energy equation, but before that let me write in a concise form, in a del operator form, in a vector form. You can also write this equation as, you see, rho into d dt of v or dv dt is equal to these two quantities minus del p del x I plus minus del p del y j can be written in a del operator by grad of p, and this quantity you see that we can write as Laplacian. This Laplacian operator is nothing but del 2 del x2 plus del 2 del y2. Okay, so we can write this quantity as del 2, here this term is del 2 u, this quantity is what? This quantity is del 2 u, this quantity is del 2 v. Okay, so this quantity in a vector form, when you add them, so it is del 2 v. Okay, plus last term is simple rho g. So this is the concise form written in terms of del operator in a general vector equation. This is what is the Navier Stokes equation. Okay, so next class we will see the energy equation.